Good afternoon, ladies and gentlemen. In the last class, we had looked at vectors in terms of the resolution of vectors in the x and y components. And if you remember very well in that class, we mentioned that the main reason why we were looking at vectors was to be able to apply them to two-dimensional kinematics. In this particular class, we are now going to apply the knowledge of vectors that we acquired in the previous class to two specific examples. The first example that we are going to take is that of projectile motion. The next example that we'll take in this class is that of relative motion. Okay, so for now, our interest is in projectile motion. So before I proceed in this with this lecture slide, just allow me to show you a certain simulation on projectile motion. Okay, so with me here, I have a cannon. I have this cannon that I can orient in any given direction. But to start with, let me orient this cannon vertically upwards, and then let me shoot. Let me shoot. So as you can see from this animation, this cannonball here is going. I'm shooting it vertically upwards. It goes up until it reaches its maximum height, and then it comes down. So as you can see, if I shoot this cannon vertically upwards, what I have is an example of one-dimensional free fall. What I have is an example of one-dimensional free fall. Okay, so, why am I saying one-dimensional free fall? Because as you can see, this cannonball or this object is just moving in one dimension, which is the y-axis. Now let me try to position this cannon at a certain angle with respect to the horizontal. Let's say I position it at an angle of 50 degrees, and I do the same thing. Let me fire it. Let me now fire it. Okay, so and then it reaches. Okay, so now what you can see here is that as this object is moving along the x-axis, as it is moving along this x-axis, it is also moving along the y-axis. As it is moving along the x-axis, it is also moving along the y-axis, which means that this object is undergoing a motion in two dimensions. But then what kind of motion is this? If you look very carefully, you realize that after I have fired this object here, when it leaves the cannon, when the cannonball leaves the cannon, as it passes through the air here, if you neglect air resistance, then you can assume that there is no other force that is acting on it apart from the force of gravity. And therefore, we can say that the object is undergoing a two-dimensional free fall, because if you remember very well, we had defined a free fall as just a kind of motion where the only force that influences the motion of the object is the gravity. So this object here, if I project it at a certain angle, it undergoes a two-dimensional free fall. Now, in physics, a two-dimensional free fall is referred to as projectile motion. A two-dimensional free fall is referred to as projectile motion. All right, so now you can see that an object that is undergoing projectile motion is following a certain path. There's a certain path that it is following until it lands on the ground here. Okay, so this path here that is followed by the projectile is called a trajectory. The path that is followed by an object is called the trajectory. Okay, so now what can you notice about the trajectory of a projectile? The trajectory of a projectile is always a parabola. It is always parabolic in shape. You can see, let me try again. I try to shoot it at an angle, this time 70 degrees with respect to the horizontal. If I shoot it there, you see it comes in, no, it follows this particular trajectory. It is undergoing projectile motion. By the way, the object that is undergoing projectile motion is called a projectile. And as we had mentioned already, I repeat, a projectile always follows a parabolic trajectory. Okay, so you can see some of the features. Let me try to point out some of the features of the projectile motion. You can see the horizontal distance that has been covered by the object is called the range. The horizontal the distance that has been covered is called the range. And then as the object rises, it reaches its maximum height, and then it starts falling due to the effect of gravity. All right, now as you can see, this projectile, it is not only on ground level where I can project it. I can choose to project it at a certain height. Let us say from the top of a certain building, I can still project this projectile. Okay, so you see I've decided to project it at a height of 11 meters with respect to the ground. It will still be a projectile. See, it follows that kind of path until it lands on the ground. Okay, so this is still a projectile motion. There is also a special case that I want to show you, a special case where I can shoot this projectile horizontally with respect to the x-axis. So you see the angle that I'm making here is 0. So if I shoot here, I can set the speed at which I want to shoot it. In this case, maybe let me just say I want to shoot it at 14 meters per second. And then I shoot. You see this is the path that this projectile has followed. And you can see from here, I can find the range. So the range is somewhere around 17.2. That is the horizontal distance that this projectile has covered. Okay, so now let us try to look at some of the things, some of the other aspects that are associated with projectile motion. So let me say that I'm shooting this projectile, say from this level. I have its initial velocity at 14 meters per second. I can change it to my liking, and I have actually removed, I've assumed that air resistance is negligible. Now I want to be able to see, let me just put it on slow so that we are able to see it properly. Okay, so if I shoot this projectile, in this manner, so it is very slow, so I pause it at that particular point. So in this case, I just want to see what is the velocity, in what direction is the velocity. So you see that at any given point, the velocity vector is tangent to the trajectory. At any given point, the velocity vector is tangent to the trajectory. So look, at any given point, the velocity vector is tangent to the trajectory. Okay, so now let me try also to, so now this velocity vector that is here, you can resolve it in the x component as well as the y component. So let us just try this velocity vector here can be resolved into the x component. You see it has got an x component, it has the y component in such a way that the resultant is somewhere here, which is tangent to the vector. Okay, so I'm very much particularly interested in these components when I'm dealing with projectile motion. Okay, so the other thing that I want to show you is that maybe let me just go down a little bit. So you see that at any given point, the velocity vector is in this direction, but then the components, this can be resolved into the x component and the y component. So at any given point, you can find it. At any given point along the trajectory, you can find the x component and the y component. The other thing that I want to point out to you are the forces. What are the forces that are acting on the projectile as it is in flight. Okay, so you see, since this object is undergoing a free fall, it's a two-dimensional free fall, it means that the only force that is acting on it is that due to gravity. So you see that the only force that is acting on it is due to gravity, and along which axis is it? It is along the y-axis. So this acceleration vector, you see, let me show you the acceleration vector. You see the acceleration vector is this one. So the acceleration of this object is in the direction of the force of gravity, which is downwards. And as you can see, this acceleration is purely vertical. It has got no horizontal component. So this is one of the most important things to take note of. The acceleration has got no vertical component. It has got no horizontal component. It only has a vertical component. Okay, so since we have seen now what projectile motion is, now let us go back to the slides and then try to analyze very carefully this projectile motion, how we can treat projectile motion in terms of those equations of kinematics that we had seen in the previous lessons. Okay, so just to go a little bit ahead, when we go to the lecture slides, we are going to see that projectile motion can be analyzed by considering the components of the velocity as well as the components of the acceleration separately. So in short, we use the same equations of kinematics that we used in one dimension, but then in those equations, what we only consider are the components. Okay, so let us now go back to our slides. Okay, so this is the general case. This is the general case of projectile motion as we had seen in the simulation. You can see that the projectile is projected from this point, which is the origin, with an initial velocity of v0. And this initial velocity could be broken down into components. We have the x component in this direction and the y component in this direction. And at any point on the trajectory, you can see that the velocity vector is just the resultant of the x component of the velocity and the y component of the velocity. So it means that as long as you have the x component of the x component of the velocity and the y component of the velocity at any given point, you can find the resultant velocity at that given point. There's something interesting that happens at the highest point, at the maximum height on the trajectory. You can see that the velocity vector is purely horizontal. The velocity vector is purely horizontal. So what does that mean? It means that the y component of the velocity is equal to 0. As you can see, this velocity here does not have any y component. This is very, very important, and it turns out to be very useful in problem solving. Okay, so at any given point along the trajectory, the acceleration is that due to gravity, and it is pointed downwards, because you know this is basically a two-dimensional free fall. Okay, so so now our next thing is we want to see which equations will be able to govern projectile motion. Okay, I just want to remind you of something to say, recall. You remember those three equations that we had derived, the three equations of kinematics. The first one, final velocity is equal to initial velocity plus acceleration times time. The second one, x is equal to x naught plus v naught t plus half at squared. The third one is final velocity squared is equal to initial velocity squared plus 2 times acceleration, and then x minus x naught. So you remember these are the three equations that we had before in one dimension. So I'll call this my equation 1, call this my equation 2, and then I'll call this my equation 3. So what I now want to do is to see what these equations will become. What I want to do is basically to see what these equations will become if I consider only the components. Remember, for projectile motion, we only consider the components of the motion. So let me see on this side. Let me say on this side, I have the x motion. On this side, I have the y motion. Just to remind ourselves, in the x motion, the acceleration, the x component of the acceleration is equal to 0. And then along the y-axis, the y component of the acceleration is equal to minus g if I consider up as my positive y. Remember, the acceleration due to gravity is purely along the y-axis. It is actually downward. So if I consider up, the up as positive, then the acceleration, the y component of the acceleration will just be nothing but minus g. Okay, so now with that in mind, let me try to look at these three equations on the x-axis. So the first equation, which is equation 1, will become Vx, meaning that the x component of the final velocity will be equal to the x component of the initial velocity. Remember, the acceleration in this case, the x component of the acceleration is equal to 0, so this entire term will just be equal to 0, so I can as well forget about it. So the equation that I have is just this one, which tells me that the x component of the final velocity is just equal to the x component of the initial velocity. Okay, so this equation basically is telling me that as far as the x component is concerned, the velocity is constant at all times because the final is equal to the initial. So as far as the x component is concerned, look at this diagram. Here, if I have the initial, the x component of the initial velocity, it means that it will be the same as this one. It will be the same as this one at all given points until it reaches there. Okay, let me now look at the second equation. The second equation tells me that x is equal to, now this x naught, if this motion is starting from the origin, such as this one here in the origin, the coordinates here are 0, 0, it means that the x coordinate is equal to 0 and the y coordinate is equal to 0. So this guy is nothing but 0. And then I just have the x component of the initial velocity times the time. I'll not say x component of the time because time is a scalar. And then look at this one also. The x component of the acceleration along the on the x-axis, we see it's equal to 0. That makes this entire term to die out. So this is basically the second equation that I have, which tells me that the distance that is covered on the x-axis, which is the range, is just equal to the x component of the initial velocity times the time. Okay, so I'll call this my equation 1 along the x-axis, and then I call this my equation 2 on the x-axis. Look at the third equation. The third equation, it tells you that Vy squared, it's Vx squared must just be equal to V naught x squared. See, I'm saying the x component of the final velocity squared is equal to the x component of the initial velocity squared. As usual, this acceleration here is equal to 0, so this term just becomes equal to 0. Now, this implies that if I take square roots on both sides, then this just becomes Vx is equal to V naught x. If I take square roots on both sides, you can see this equation is not different from that. This equation is just the same as that. So it means that this third equation is not giving me anything different. So I can as well just remove it because I already have that equation. So on the x-axis, these equations of kinematics, I'm only getting two important equations, the first one here and the second one here. Let me come to the y-axis. The first equation on the y-axis will look like this. Vy must just be equal to V naught y. Now, what is my acceleration? My acceleration on the y-axis is minus g. So where there was acceleration, I'm going to replace that. So it just becomes gt. So this becomes my first equation on the y-axis. What about the second equation where there was x? I'm going to replace the y because I'm now in the y-axis. And then as before, this y0, the y0 is equal to 0 since I'm starting from the origin. And then this guy becomes v naught y, the y component of the initial velocity times the time. And then here I have minus half gt squared. Where this g is coming from, remember the acceleration here is nothing but minus g. Similarly, the third equation just gives me vy squared is equal to v naught y squared minus, remember this acceleration again is the minus g, and then this is this x naught is now equal to y naught, which is equal to 0 since I'm starting from the origin. Then I just have 2gy. So this is my second equation on the y-axis. This is my third equation on the y-axis. Okay, so this set of equations now makes up my tools box that I have to use when dealing with these equations. So whenever I am faced with a problem on projectile motion, I should come to these equations and look at and try to see which equations will be best suited for that particular problem. Okay, so this slide is just a summary of what we have already done. You see on the horizontal motion, where we have said that the x component of the acceleration is equal to 0, we saw that the x component of the velocity is a constant, and then this is the set of equations that we are going to use along the horizontal component. In a similar way, along the vertical component, along the vertical motion, these are the equations that you are going to use when dealing with projectile motion. All right, so now let us look at an example. Try to apply this knowledge that we have gathered and try to apply it to this example. Okay, a football is kicked at an angle theta not equals 37 degrees with a velocity of 20 meters per second as shown. So we have a diagram here that has been drawn for us. We are lucky that a diagram has been drawn, but ordinarily we might not be given this diagram. We might be required to come up with a diagram on our own. Well, so the question says that calculate the maximum height, the time when this ball hits the ground, part C, the total distance traveled in the x direction, part D, the velocity at the top, then part E, the acceleration at the top. So let us try to do this problem step by step. Let us try to do this problem step by step. So the first thing is that I'm going to draw a diagram. I'm just simply reproducing that diagram that has been drawn. So this is the y-axis. I've considered up as positive. This is the x-axis. Okay, so the origin is here. And from the origin, I've been told that I've decided to take the point at which the football is kicked as the origin. So the football is kicked with this. The football is kicked with this velocity, and then of course it is going to take this trajectory up until it reaches this point. Okay, so we have been told that this is the initial velocity. We have been given the value. Say that the initial velocity is nothing but, I think it was 20.0. Just go back and check. The initial velocity was 20.0 meters per second. Okay, and then we're given that the direction, the angle theta naught, the angle theta naught was given to be 37.0 degrees. Okay, so you see that this velocity here can actually be broken down into the x component of the velocity here and the y. And the y, let me draw the y in a different color since I have these colors. So the y component is from there to there. So I have this x component, which I'll call v naught x, and then I have this y component, which is v naught y, the y component of the initial velocity. Okay, so since I have the magnitude of the initial velocity, I also have the angle. It means that I can actually find what these velocities are, v naught x. Remember from our issue of vectors, will just be given as v naught and then cos theta naught. Okay, so if you put in the numbers, it is 20.0 meters per second, and then times the cosine of 37 degrees. Okay, so if you work this one out with your calculator, v naught x, I'm sure you may find that it is about 16.0 meters per second. So we have found the x component of this guy, the x component of the initial velocity. In a similar way, let us find the y component of the initial velocity. It will just be given by v naught sine theta naught. If you put in the numbers, v naught is 20.0 meters per second. You just multiply it by sine 37 degrees. You try to work this one out using your calculator. You find that this may give you something like 12.0 meters per second. So here, this is the x component. This is the y component of the initial velocity. So I haven't started solving the problem yet. So far, I've just been trying to prepare myself to do the problem. So now, let us look at part A of the question. It says that find the maximum height. Find the maximum height. So in part A, I have to find the maximum height. So in this case, I'll have to go back to my tools box that I have made for myself here. So the maximum height is basically going to be along the y-axis. The maximum height here is basically just along the y-axis. So it just corresponds to the position on the y-axis. What is the y-coordinate of this ball when it is at the maximum position? Remember, the maximum position corresponds to Vy is equal to 0. The y component of the velocity there is equal to 0. Very, very important. So you go to those equations that you have. You see that in this equation, you don't have any y. You don't have any y. And then in this equation, you have a y. But the problem is that you don't have the time. You don't have the time. You have not been given the time. And then look at this third equation. In this third equation, of course, you know at the maximum height, this is equal to 0. And then the initial velocity, you already have it. If you remember very well, it was about 12. The y component of the initial velocity was 12 meters per second. So you have it. And then g is a constant. And then this y is what you are looking for. The y is what you are looking for. So we can actually use the third equation and apply it to that particular situation. So I'll say we are using this equation. Y is equal to v naught y. Sorry. The equation that I'm actually using is this one. Vy squared is equal to v naught y squared minus 2gy. Okay, so what information do I know? The information that I know is that at the maximum height, my y component is basically equal to 0. So it means that when I set Vy is equal to 0, then this y will be equal to y max. So let me do that. So I have 0 here is equal to v naught y squared minus 2gy max. Remember, because I've put a 0 here, then this y must actually be y max, which corresponds to the maximum height that this projectile reached. So if I make y max subject to the formula, then I'll skip some steps that I think that are very basic for you guys. So I make y max subject to the formula, then I'm going to have v naught y squared over to g. If you just make this y subject to the formula by taking it this other side and dividing throughout by 2g, then you find that I have this equation, which is actually my symbolic answer. You know that I have everything here. I have v naught y is just nothing but 12, and then g is a constant. So you can substitute these, and then you find your answer. Okay, so this is just basically 12.0 meters per second, and then you square this because this is squared, and then you divide by 2 times g, which is 9.8 meters per second. So I'll leave it here, and then you guys, you can work out what the answer will be. Look at the second equation. Find the time when the ball hits the ground. Find the time when the ball hits the ground. So the trick there, the strategy that I'm going to use there is that I know the distance that has been covered up to the maximum height. Okay, so I know the distance that has been covered up to the maximum height. And the other thing is that I know the velocity at the maximum height is equal to that. The velocity at the maximum height is equal to that. Okay, and then I also know the initial velocity that has been given. So let us look at our tools box. We go to our tools box again, and then here you can see in this equation at the maximum position we have this is equal to 0, and then you remember we have the y component of the initial velocity. It is about 12 meters per second. So the only thing that we don't know is the time that it takes to reach the maximum height. So we can calculate this time that it takes to reach the maximum height. Let me show you on this diagram. So if we calculate the time that it takes to reach the maximum height, then I can simply multiply that by 2, because you see from the symmetry of the problem, the time that it takes for the ball to move up to this position is the same as the time that it takes for it to move across up to the ground level. So if I find the time that it takes to go to the maximum height, I just multiply it by 2 in order to get the total time. So that's basically what I'm going to do in part B. Okay, so part B, I'm using this equation. Vy is equal to V naught y minus, V naught y minus GT. Okay, so again, I'll say that at the maximum height, at the maximum height, I know that my Vy, the y component of the velocity, is equal to 0. Okay, and then it also implies that this time, the time here will just be equal to T1. I have denoted T1 by the time that it takes for this object just to move up to the maximum. So eventually I'll have to multiply it by 2, as I had already indicated. So let me now put everything in this equation. It becomes 0 is equal to V naught y minus GT. Okay, and then I can make T subject of the formula. T is basically nothing but V naught y over G. Okay, so this equation here, it will actually give me T1 because I have my V naught y. So I have my V naught y. So this T1 here, I can now multiply in order for me to find the total time. I can simply just multiply this by 2. So total time, if I can call it T tot, is just equal to 2 times T1. You see, T1 was given by this equation, so I can just say 2 times V naught y over G. So this equation is basically the equation that I'm going to use to find the time. Remember, V naught y was basically 12 meters per second, and then G is basically 9.8 meters per second squared. You try to put this in here in this equation, then you realize, I think, just give it a try. I think you may find that you have 2.45 seconds. So this 2.45 seconds is basically the time that it took for this ball, after it had been kicked here, to go up there and then to come back to the ground level. Okay, so part C of the problem, requires us to find the total distance traveled in the x-axis. So the thing here is that we are in the x direction. So if we go back to our equations, on the x motion, we find that the most appropriate equation to use is this one, because they are looking for the total distance along the x-axis. So what do we have? We have this V naught x. Remember, V naught x is one of the things that we have. If I remember very well, it was about 16.0 meters per second. And then the time, the total time that it takes, I think it is just what we are from finding to be about 2.45 seconds. So already we can see that we can actually calculate the total time, the total distance that this projectile covered along the horizontal axis. So part C, it's just basically talking about the range. What was the range of the projectile? I'm using this equation, V naught x times t. What is the data that I have? V naught x, remember from the data, it was about 16.0 meters per second. And the time is what I just found now to be 2.45 seconds, 2.45 seconds. So it means that the range, it will just now be 16.0 meters per second, which is my V naught x, times the time, 2.45 seconds. You see this seconds and that one cancels. So basically this will be just in meters. All right, so you can try and multiply this. Try to multiply this in order for you to find the total range, the total distance that was covered in the horizontal axis. You can use your calculator. If I remember very well, I think, let me just try to punch my calculator here. So I have my calculator. So I have 16 times 2.45. So it is actually giving me 39.2. Giving 39.2 meters. So this was basically the distance that was covered along the x-axis. Okay, so what about this? What is the velocity at the top? So at the top, what is the velocity at the top? So one thing that we have mentioned already is that at the top, it is important to know that the y component at the top was 0. So and then the x component, remember the x component is always constant. So you see this part D, what do I know? I know that V naught y at the top is equal to 0. And then what about the Vy at the top is equal to 0. What about Vx? The x component of the velocity is just equal to the x component of the initial velocity. Remember, we had said that the x component doesn't change. So it's equal to the x component of the initial velocity, which we know very well to be 16.0 meters per second. Okay, so now if you have the components of a vector, you can actually find the vector itself using Pythagoras Theorem. So this v is just vx squared plus vy squared. This is basically just Pythagoras theorem. So if you put the numbers there, you find vx squared 16.0 meters per second. You are squaring this, and then plus 0 squared, which will just be equal to 0. So if you compute this, then you realize that the velocity will just be 16.0 meters per second, which is actually equal to just the x component of the velocity, which was expected because you know at this maximum point, the velocity is just equal to the x component of the velocity. All right, so that is actually the velocity at the maximum point. In a similar way, you can actually find the acceleration. What is the acceleration at the maximum point? So you find the components. The x component of the acceleration is equal to 0. Remember, the x component is always equal to 0. What about the y component of the acceleration? It will just be equal to minus g along the y-axis. So if you have to find the acceleration itself, the magnitude of the acceleration, then you just have this squared plus that squared. Okay, if you put in the numbers, then this is just 0 squared plus this one minus g squared. Of course, if you evaluate this, it will just give you g. That is the magnitude. And what is the direction? The direction is the downward. Okay, the direction is downward. So if you have this as your x, y plane, xy coordinate system, then the direction of the velocity, the direction of the acceleration, it will just be downwards. So what is downwards? If you want to express it in terms of an angle, then you can see the angle is this one. So it means that the theta, the angle is just 270. Remember, here this is 90 plus 90 plus 90, it gives you 270. Or if you want, you can say the theta is equal to, remember clockwise, if I go clockwise in this direction, then it is negative. So I can say theta is negative 90. So the magnitude is g. Remember, g is 9.8 meters per second. That's the magnitude of the acceleration. The direction is, you can either write 270 degrees or minus 90 degrees. And by the way, I must also mention about the direction of the velocity in part D. I think I forgot to take care of the velocity. The magnitude of the velocity, since we had said that the velocity, you see, it is horizontal, meaning that what is the direction? With respect to the positive x-axis, the direction is equal to 0. So under here, I'll just say that theta is equal to 0 degrees because I have the magnitude and the direction, and the combination of these things gives me a full vector. Okay, so this, ladies and gentlemen, is the way we apply those equations of kinematics in order to solve problems on projectile motion. This is how we apply those equations to solve the problems on projectile motion. Okay, so the next thing that we are going to do, ladies and gentlemen, is to consider another example of two-dimensional kinematics. The first example that we had looked at was that of projectile motion, which we saw that was nothing but a two-dimensional free fall. And in that case, we saw that the issue of vector resolution, resolving vectors into components, became very, very handy. Okay, so as the second example of two-dimensional kinematics, we are going to look at the issue of relative velocity. Just to remind ourselves, I think in the previous lecture, we had looked at relative velocity in one dimension. For instance, if you have two trains, you have this, let us call it train 1, this one, let us call it train 2. So train 1 is moving with a speed of 95 kilometers per hour to the right. So it means that this is positive 95 kilometers per hour, assuming that we have taken right as the positive x-axis. And this train 2 is moving to the left at the same speed of 95 kilometers per hour, which means that this is the negative velocity, since it's moving to the left, which is opposite the positive x-axis. So with respect to this, with respect to train 1, if you are in train 2 and you are looking at train 1, with respect to the observer in train 2, train 1 is moving at a speed of 95 plus 95, which is 190 kilometers per hour to the right, which is positive. And with respect to train 1, it means that train 2 is moving at a speed of 190 kilometers per hour to the left, which means that it is negative 190. But with respect to someone who is on the ground, these two trains, train one here is moving at positive 95 kilometers per hour. Train 2 is moving at a speed of negative 95 kilometers per hour since it is to the right. So the point here is that the velocity of an object depends on the frame of reference from which you are observing that object from. Okay, so that is what relative motion is all about. Now, we want to apply this relative motion to a two-dimensional case where the object is not only moving in one dimension, but it is actually moving in two dimensions. Okay, so before we proceed, I just want to show you a certain simulation. I want to show you a certain simulation so that probably it would be able to assist in your understanding of this two-dimensional relative motion. Okay, so in this, this is just basically a simulation that I just want us to do together, hoping that it will help in you grasping this concept of relative velocity. Okay, so what I have here is a river. So I have a river here. You can see that this river is flowing to the eastern direction, and then I have a boat. So this boat is on this other side of the shore, and then its target is this. It actually wants it to move up to this point here, this red point. Okay, so now you can see that the river, this is the velocity of the river with respect, if I'm standing on the shore, I will observe the river to be moving with a certain velocity to the right in the eastern direction if I'm standing on the shore. Okay, so you see I can adjust this to anything that I want. I'll show you how it works. So I can adjust this to anything that I want. The other thing that I can adjust is the speed of the boat. So the speed of the boat, I can also adjust it to anything that I want. Okay, now if I, let me just show you something. Let me just show you something. If I make this river, I say that this river is not moving. It is just like a pool of water. Okay, see, and then let me run. You see what is happening to the boat? The boat is just moving straight. The boat is just moving straight until it reaches its destination. It reaches its target on the other side of the shore. Okay, now let me try to increase the velocity of the river. The velocity of the river, this side I've put it to be maybe at 3.1. Let me just try to put it at 3. So I've put the velocity of the river at 3 meters per second. Now, do you think that this boat will just move straight to the other side? Okay, so let us see now what will happen in this particular case. Let us see what happens in this particular case. So you see the boat, its target is to go there, but then there is also the river that is flowing. Okay, so this boat is being drifted on the other side. It's being drifted on the other side until it reaches. So you see that the boat, if it targets this, if the nose of the boat is directly upwards, it means that it will not reach this target. It will actually reach at that particular point because of the drift of the river current. Okay, so let us try to do this experiment again. Let us try to do this experiment again. So this boat is moving, it's moving, it's moving. Okay, so let me pause at that particular point. So I pause the boat. And then let me show the vectors that are acting there. So it means that you see the boat itself is moving upwards. The boat is moving upwards, so it is pointing in this direction. But then the river is also moving to the right in this direction. So this is the velocity of the river with respect to the earth. So someone who is standing here will see the river moving in this direction. So it means that since the boat will move in a direction since the boat will move in the direction that is a resultant of these two vectors, as you can see, it will actually move in this direction. So the resultant motion of the boat, it will be drifting in this direction, in the direction that is a resultant of the boat's velocity and the river velocity. All right. So, and then, so let me just continue running until it reaches at that particular point. Until it reaches at that particular point. Okay, so let me do it again. I've now set the velocity of the river with respect to the f. The velocity of the river is moving in this direction with a speed of 2 meters per second. And then I've set the velocity of the boat with respect to the river. The velocity of the boat with respect to the river as 2.9 meters per second. And then this boat is pointed at an angle just towards the north, directly towards the north. So I run again. So you see there is drift. This boat is drifting to the right until it touches the shore at that particular point. So you see, this is not the point where this sailor wanted to go. This sailor instead wanted to reach this point. Okay, so in order for this sailor to reach this point and not this point, okay, it means that they need to point the nose of the boat at a certain angle. So they need to be sailing in this direction. It means that the velocity of the boat with respect to the river must be somewhere along this direction, so that as they are sailing this direction and the river is moving in this direction, then they'll be able to land at this particular point. Okay, so let me just try it one more time. Let me change the angle here, the direction of this boat. Maybe let me try to put it at, negative 30. Okay, so it means that this guy is somewhere there. The boat is pointed at that particular direction. Let me try it again and see whether this guy will now reach this point. So if I start running, you see they are getting there, but then the drift is a little bit too much. It's a little bit too much until they reach. They are a little bit close, but they are not at the exact position that they wanted to be. So in order for this sailor here to be at the position where they wanted to be, they need again to sail further in this direction. So let me try to increase that angle. Maybe I just increase it to 40, to 44, and then I try. Okay, so you see they are going. The river is pulling in this direction, but they are also headed in it, and then right there. Okay, so if the boat is pointed at this angle of 44 degrees west of north, 44 degrees west of north, that is the only time when the boat will be able to cross to the point which is directly opposite to the point where it was on the other side of the river. Okay, so basically there, what are you seeing here? It is just basically an issue of vector addition. You see the velocity of the boat. This is the velocity of the boat now with respect to the river. You see it was pointed in this direction. So the velocity of the boat with respect to the river, and then the velocity of the river with respect to the boat, to the S, is in this direction. And then in that way, we have the resultant, which is directly upwards, so that this boat will be able to sail directly up to this point. So in short, this is an example of vector addition. We are trying to add the relative, we are trying to add vectors in order to come up with the relative motion. Okay, so with this background now, let us go back to the slides so that we see now how to we just try to put together everything that we have seen here. Okay, so in the discussion of relative velocity, there is a certain convention that we usually use, where we use these subscripts. Okay, so for instance, if we are talking about the velocity, the first subscript represents the object that is in motion. The second subscript represents the frame of reference with which we are measuring this velocity. For instance, look at this. We know that there is a boat that is moving in a river. Okay, so if we say VBS, that means we are referring to the velocity of the object. The object that is moving in this case is the boat, and then the frame of reference is the shore. So this VBS represents the velocity of the boat with respect to the shore. And what it means is that when the observer is standing on the shore here, this represents the velocity with which they'll observe the boat to be moving at. In a similar way, this here can be read as the velocity of the boat with respect to the water. So it means that if the observer is moving together with the water, then this is the velocity that they observe for the boat, which is the object. The object here that is moving is the boat. In what frame of reference? In the frame of reference of the water. Okay, so now how do we implement this? You see that, for instance, if this is the velocity of the boat with respect to the shore, okay, you can see that the velocity of the boat with respect to the shore, this vector here is just the resultant of this vector here plus this vector here. In other words, this velocity here, the velocity of the boat with respect to the shore, is just the vector sum of the velocity of the boat with respect to the water and the velocity of the water with respect to the shore. Okay, so in short, we write the velocity of the boat with respect to the shore is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. Now, there's something that you can note from this equation here. If this equation of relative motion here is written correctly, the first thing that you see is that look at this outer subscript. The outer subscript here represent the resultant here. You see here the boat with respect to the shore is the same as here on the outer part you have the boat, and here on the outer part you have the shore. You know, again, you can look at the inner subscript. The inner subscript, this one and this one are basically the same. This one and this one are basically the same. So this is what tells you whether the equation that we have written is correct. If the equation that you have written is correct, then the outer subscript will give you the resultant velocity, and the inner subscript will basically be the same. Okay, so let us try out an example. And see how we can apply this to a problem. Okay, so the problem reads: a boat's speed in still water is 1.85 meters per second. If the boat is to travel directly across a river whose current has a speed of 1.20 meters per second, at what upstream angle must the boat be headed? At what upstream angle must the boat be headed? So let us try. Okay, so a boat's speed in still water. A boat's speed in still water is VB. So the data that I have, let me write. Okay, a boat's speed in still water is W is equal to 1.85 meters per second. That is the data. So the velocity of the boat with respect to the water is 1.85 meters per second. If the boat is to travel directly across a river whose current has speed V WS, the velocity of the water with respect to the shore, given by 1.20 meters per second. Okay, so the question is that at what upstream angle must the boat head? At what upstream angle must the boat head? So let me just draw a simple diagram here. So I have the river. This is the river, and then I'm assuming that this river is okay. So let me first of all say that this is the point where the boat is starting off. This is the shore, and then this is the other part of this is the other, the opposite side of the river. So the boat is starting off at this place, and it is targeting this point that is directly opposite. Okay, so we have been told that if the water is still, if the water was still, then the boat will just move straight like that. Okay, so in short, this is basically my the velocity of the boat with respect to the water. This is when the water is just still. The other aspect is that I have a river current. Let us say that the river current is in this direction. So this is the water current of the river is in this direction. So this is the velocity of the object that is moving is the water. And then with respect to what? The water is moving with respect to someone who is standing by the shore. This is the velocity of the water with respect to the shore. So what is the resultant of this? So in order for the boat to touch this point, as we had seen in the simulation, in order for the boat to touch this point, then it must be set off at a certain angle, in that particular direction, so that this drift, the drift of the river current, will make the boat to drift in this direction, and then eventually it will reach that targeted point. So I'll say this is the velocity of the boat. The object that is moving is the boat. Now, with respect to what? With respect to the, sorry, I think this should be the velocity of the water with respect to the shore. Okay, this is the velocity of the water with respect to the velocity of the boat with respect to the shore. Okay, the velocity of the boat with respect to the shore is what has been given, because with respect to the shore, the velocity is just, the boat is just moving vertically like that. And this one that is here is the velocity of the boat with respect to the water. The velocity of the boat with respect to the water. Okay, so let me try to put this together into an equation. You see, in order for this vector here is just the resultant of two vectors. The first vector is from there to there. The second vector is from there to there. In short, I'm saying that for someone to move from here up to there, it is as good as they first move up to that point, and again they make some movement up to that particular point. So we are saying that this VBS is equal to VBW plus VWS. Okay, VBS, the velocity of the boat with respect to the shore, is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. You can note that these two are the same. The inner subscripts are the same. Look also at the outer subscript. This guy is the first one, then this guy is the last one. Okay, so the question, what is the question asking for? The question is asking for the angle. At what upstream angle? So it's actually asking for this angle that is here. Now, look, this angle that is here basically is connecting, you see, with respect to this angle, what has been given is this VBS, which has got a value of 1.85. The other thing that has been given is this guy. So with respect to this angle, you can see that this is the adjacent side and this one is the opposite side. So we can say that tan of theta is just basically equal to the opposite, which is VWS, over the adjacent, which is VBS. You can actually put now, and then you can say the theta then is just basically the tan inverse of VWS over VBS. Now you know what all these angles are. I think you know what all these angles are. You have been given in the data. So the theta that you're actually looking for is just tan inverse of VWS, which is 1.20 meters per second. And then the VBS is 1.85 meters per second. So these can cancel out, and I think you can now work out. You can work out this angle, since you can just evaluate it using the. You can evaluate it using your calculator in order to find the angle. And then if you find the angle, that is the angle at which the boat must be headed. If you want, you can even find the standard angle. You can actually find the standard angle by just subtracting this angle that you have found here from 90 in order to find this one, which is actually the standard angle. Okay, so so basically this is how you work out this problem. And actually you can even do something additional. If the question also asks you for what is the velocity of the boat with respect to the water, it will be very easy, since now you have this angle here that you have found from there. Then you also know this one and this one. Then you can just say what is the relationship between this and that. Okay, what is the relationship between this and that? You know, with respect to this angle, this is the adjacent and this is the hypotenuse. So the adjacent and the hypotenuse. So you can say that cos of theta will just be equal to the adjacent, which is VBS, over the hypotenuse, which is just VBW. So if you have been asked to find the velocity of the boat with respect to the water, then you say velocity of the boat with respect to the water is just equal to the velocity of the boat with respect to the shore, which you know is 1.85 over the cosine of theta. You remember theta, you have already evaluated it here, so you can actually just find the cosine of this, and then in that simple manner, you can actually calculate the velocity of the boat with respect to the water. The same boat, VBW equals 1.85 meters, now heads directly across the river, whose current is 1.20 meters per second. A, what is the velocity, magnitude, and direction of the boat relative to the shore? And then part B, if the river is 110 meters wide, how long will it take to cross, and how far downstream will the river be then? Okay, so as before, let us try to draw a very simple diagram. So this is the river, this is the shore, and then this is the other side. And then let us assume that the river is starting out at this particular point. But then note, in this case, we've been told that the boat now heads directly across the river. It means that it doesn't make any angle. It now heads, if it wants to target this point on the other side, then it just heads in this direction. So the boat heads in this direction. So we'll say that this is basically the velocity of the boat with respect to the water. Okay. Now, since the river is in this direction, since the river, the velocity of the water with respect to the shore is in this direction, it means that the boat will now be drifted. The boat will now be drifted in this direction indicated here, such that it will, if it goes in this direction, then it will touch the shore at some distance here. Okay, so let us call the width of the river. Let us call the width of the river from here up to here. Let us call it capital letter D, and then let us call the distance that it lands on the other side of the shore from the point that was targeted. Let us call it small letter D. Okay, so then what is our data that we have been given? The data is that the velocity of the boat with respect to the water is 1.85 meters per second, and then the velocity of the water with respect to the shore is still 1.20 meters per second. And part A of the problem is saying that what is the velocity of the boat relative to the shore? So what is the velocity of the boat with respect to the shore? That is what we are looking for in part A. So you can see from the diagram, this is the velocity of the boat with respect to the shore. Okay, so this is very simple, since you know from this is the angle that has been given. So you know from Pythagoras Theorem, this is the adjacent, this is the opposite, and then this is basically the hypotenuse. So we can use Pythagoras Theorem just to find the hypotenuse, in this case, VBS, that is the magnitude of the velocity of the boat with respect to the river, can just be given as the velocity of the boat with respect to the water squared plus the velocity of the water with respect to the shore squared, and then we take the square root of everything. This is basically just nothing but Pythagoras theorem. So VBS is just nothing but the square root of, now we have the data there, which is 1.85 meters per second. So we have to square this one plus this 1.20 meters per second. We also square this one, and then we take the square root. Okay, so when we calculate this, when we compute this with the calculator, we find that the magnitude, just try to do it on your own just to confirm, will be 2.21 meters per second. So this is the magnitude of the velocity of the boat with respect to the river. And what about the direction? We are just talking about this angle. You see, with respect to this angle, what we have is the adjacent, and we also have the opposite. It means that we are using the TOA part opposite over adjacent. So it means that the tan inverse of this, the tan inverse of this angle theta will just be nothing but okay. So let me write it again. It simply means that theta will basically be the tan inverse of the opposite, which is V WS, over the adjacent, which is V B W. Okay, so VWS, we have it 1.20. VBW, we have it 1.85. Just try to put these numbers in there and confirm that to get an angle of about 33 degrees. So we have answered part A of the problem. We have found the magnitude of the velocity of the boat relative to the shore. The magnitude is 2.21 meters per second squared, and the direction is 33 degrees. Okay, so let me just try to help you with part B of the problem. Part B says that if the river is 110 meters wide, how long will it take to cross, and how far downstream will the boat be then? So in short, first of all, we want to find the time that it takes in order for the boat to move across to the other side of the river, and also to find this distance here. How the second part says that how far will it be downstream, meaning that what is this distance here? So the trick to this is just to realize that with respect to the vertical axis here, the boat is actually moving at a velocity of this, and then with respect to the horizontal, the boat is actually moving with a velocity of this. So basically, you know that in order to cross the other side of the river, the boat has actually just covered a distance of d, and then you could say that it is moving with a velocity of this in this component. Okay, so I'll use that equation for distance moved, because you know this is a constant velocity. So I'll just say that I'll use this equation. Remember, the distance traveled is just equal to the speed, the velocity. In this case, is the velocity of the boat with respect to the water, the velocity of the boat, the velocity of the boat with respect to the water, and the time. This is the time that it takes. This is the distance. So I want to find the time. I make it a subject of the formula. So time is equal to V dW over, the time is just nothing but the width of the river over V dW. And then from the data that have been given, what is VBW? VBW is nothing but 1.85 meters per second. And then what is D? D is this one, the width of the river, which is 110 meters. So when you substitute there, then you have 110 meters over 1.85 meters per second. You see these cancels, and then basically you find out, if you compute this, you find that you have a time of about 60 seconds. You have a time, just try to compute or to confirm with your calculator. You have a time of about 60 seconds. So it took about 1 minute. It took about 1 minute for the boat to move to the other side of the river. And the other part of the question says that how long will it take to cross? Okay, this one we have already answered. And how far downstream will the boat be then? So we are talking about this distance. What is this distance? Now you see along this component, the velocity is this much. And we see that the time that this object is moving upstream, the time that this object is moving up to the other side of the river, it is also covering this distance because on the horizontal component. So I will just say that in a similar way as I had that, I will say the distance that is covered there is basically just the velocity of the water with respect to the shore. The velocity of the water with respect to the shore times the time. See, the time is basically that which has been given there. Okay, so the velocity of the water with respect to the shore, it has been given as 1.2 meters per second. Let me just confirm. It's 1.20, yes, 1.20 meters per second. And the time is just what we have found to be 60 seconds. So it means that this distance D will just be nothing but 1.20 meters per second. And then times 60 seconds. So you cancel this and that, then the distance will only be in meters. You compute it with your calculator. You may find that it is basically something like 72 meters. Just try to confirm. So the distance that the boat has drifted from its target point will basically just be this much, 72 meters. Okay, so ladies and gentlemen, this ends our class for today. In summary, we have just tried to apply we just tried to apply the concept of two-dimensional kinematics to two different examples. The first example that we had was that of projectile motion, where we saw that the motion could be analyzed by treating the x component of the motion and the y component of the motion separately. And now we have just seen how to deal with. We've seen that relative velocity in 2 dimensions. We have given examples of a river current, so we could take care of these the components of the relative velocities. Okay, in terms of here we had to resolve. We had to consider the velocity of the boat with respect to the water, the velocity of the boat with respect to the shore, as well as the velocity of the water with respect to the shore. Okay, so thank you very much and enjoy the rest of your day.